Hello everyone, welcome to the course on cryptography. So in today's session we'll discuss about fermats and Euler's theorems. The two theorems that play important roles in public key cryptography are Fermat's theorem and Euler's theorem. So first we'll discuss about this Fermat's theorem. This Fermat's theorem states the following: if P is prime and A is a positive integer which is not divisible by P, then A bar P minus 1 is congruent to 1 with mod P. So considering the set of positive integers that is less than p, that is 1, 2 till p minus 1, and multiply each element by a modulo p to get the set. This is equal to a mod p to a mod p till p minus 1 a mod p. So none of the elements of x is equal to 0 because p does not divide a. Further, no two of the integers in x are equal. To say this, assume that ja is equal to ka, where j lies between 1 and k. K is again less than or equal to p minus 1 because a is relatively prime to p. So we can eliminate a from both sides of the equation, resulting in j is congruent to k mod p. This last equality is impossible because j and k are both positive integers less than p. Therefore, we know that the p minus 1 elements of x are all positive integers with no two elements equal. We can conclude that the x consists of the set of integers that is from 1, 2 till p minus 1 is in some order. Multiplying the numbers in both sets p and x and taking the result mod p gives a into 2a into p minus 1 into a which is congruent to 1 into 2 into p minus 1 of mod p. So this leads to a bar p minus 1 into p minus 1 factorial congruent to p minus 1 factorial of mod p. So we can cancel this p minus 1 factorial term because it is relatively prime to p. So this leads to the equation as a power p is equal to a mod p. So an alternative form of this Fermat's theorem is also useful. If p is prime and a is positive integer, then a power p is congruent to a mod p. The first form of the theorem requires that a be relatively prime to p, but this form does not. So p is equal to 5 and a is equal to 3, then this can be written as a bar p is equal to 3 bar 5. That is equal to 2, 4, 3. So it is congruent to 3 of mod 5. Next is Euler's totient function. So this is related to Euler's theorem. So here we need to introduce an important quantity in number theory referred to as Euler's totient function. This function, written as pi of n, is defined as a number of positive integers less than n and relatively prime to n. So by convention, pi of n can be written as 1. So determining pi of 37 and pi of 35. Because 37 is prime, all of the positive integers from 1 through 36 are relatively prime to 37. Thus, pi of 37 can be written as 36. So to determine the pi of 35, we list all the positive integers less than 35 that are relatively prime to it. So 1, 2, 3 till 34. There are 24 numbers on the list. So pi of 35 is equal to 24. So and the list, the first 30 values of pi of n. The value of pi of n is without meaning, but it's defined to have the value 1. So it should be clear that pi of p is equal to p minus 1. So for a prime number p. Now suppose that we have two prime numbers p and q with p not equal to q, then we can show that for n is equal to pq. So this shows the sum of some values of Euler's quotient function of pi of n. So pi of n can be written as pi of pq, which is equal to pi of p into pi of q is equal to p minus 1 into q minus 1. To see that pi of n is equal to pi of p into pi of q, consider that the set of positive integers less than n is the set. So the integers in this set that are not relatively prime to n are the set, and the set q to q p minus 1 into q. Consider that any integer that divides n must divide either of the prime numbers p or q. Therefore, any integer that does not contain either p or q as a factor is relatively prime to n. Further, the two sets just listed are non-overlapping because p and q are prime. We can state that none of the integers in the first set can be written as a multiple of q, and none of the integers in the second set can be written as a multiple of p. Thus, the total number of unique integers in the two sets is q minus 1 plus p minus 1. So it can be written by the expression pi of p into pi of q. So next we'll see about Euler's theorem. Euler's theorem states that for every a and n that are relatively prime, a of pi of n is equal to 1 mod n. So this is true if n is prime, because in that case pi of n is equal to n minus 1, and Fermat's theorem holds. However, it also holds for any integer n. So pi of n is number of positive integers less than n that are relatively prime to n. Consider the set of such integers labeled as r is equal to x1, x2 till x pi of n. Each element xi of r is a unique positive integer less than n with GCD xi comma n is equal to 1. Now multiply each element by a modulo n. S is equal to ax1 mod n, ax2 mod n, ax pi of n mod n. The set S is a permutation of R by the following line of reasoning. Because A is relatively prime to n and xi is relatively prime to n, axi must also be relatively prime to n. Thus all the numbers of S are integers that are less than n and that are relatively prime to n. There are no duplicates in S. If ax mod n is equal to axj mod n, then xi is equal to xj. Therefore, it can be given by the equations as shown here. So as is the case for Fermat's theorem, an alternative form of the theorem is also useful. That is, a bar pi of n plus 1 is congruent to a mod n. Again, similar to the case with Fermat's theorem, the first form of Euler's theorem requires that a be relatively prime to n, but this form does not. Thank you.